All right, guys, welcome. Let's go ahead and get started. Quick reminder before we begin. I know some of you are planning to use some late days on homework 3. If that's you, this is the last day that you can possibly turn it into me. So I need it today. I don't know if anybody is still working on it or not, but if you are still working on homework 3, you're out there, give me what you got. By the end of the day today, I will give you as much partial credit as I possibly can, but I will not accept homework 3 after today. So definitely make sure you get that submitted if you haven't done so already. Homework 4 is due next week, I believe, right? Next Wednesday. 2 weeks? The 18th. Oh, what day is it today? I don't know what day it is. Okay, so 12 days. Yeah, so almost 2 weeks. Yeah, not next Wednesday, but the Monday after that. Yeah, that sounds great. That's better. Okay, cool. So I think that about does it. Are there any questions about the current homework assignment, homework 4, or anything else that you'd like to chat about before we pick up where we left off on Monday? So actually, first thing on our agenda today is to talk about those practice problems that we left off with on Monday. And then what's going to happen after that is I do have a few loose ends I want to tie up regarding distributed databases. So we'll talk about that for a little bit. And then after that, I've got actually a whole lot more practice problems for us to talk about today. So today is going to be very practice problem heavy, I hope. That's the plan anyway. So we're just going to be doing practice all day today. Well, not all day, but most of the day today we'll be doing practice problems. That's the goal. And then just as a little heads up, on Monday we are starting something very, 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 very different. So we're going to be looking at databases still, but we're going to be switching away from SQL databases and start looking at NoSQL databases. So the one that we're going to be spending a lot of time with is Mongo. But we'll take a look at some other ones as well. And so that's going to be starting on Monday. It's very exciting, very cool stuff, but also extremely different than what we've been doing up until now. So today is kind of the last day that we're going to be talking about SQL-oriented stuff for a little while. So if you have any lingering questions or things that you'd like to talk about relating to SQL-oriented databases, relational-oriented databases, before we switch and talk about NoSQL databases, today is a good day to do that. All right, so we left off with a couple of practice problems, and they were based on this example problem that we did in class last week, last Monday. So we worked on this problem together. We did the math. We figured out that the best case for this particular situation was to send both tables to site 3 and perform the join there, I believe, right? Or what did we decide? No, it was to perform the join on site, I don't remember. Site 2? I need to go back and watch my own video. But anyhow, we have a different query to look at now. So here we see this query is a little bit different. And let's start today by kind of reviewing this concept and going over this problem and see if we can figure out what the best way to go. Actually, I don't even need that. Can I undo? Shoot. I just need the query. I don't need anything else. All right, there we go. I just need the query. So here's the query. It's submitted at site number 3. And we need to figure out then how much data needs to be sent. So there's, again, 3 options. Where do I want to perform this join? Do I want to perform this join on site 1, site 2, or site 3? So let's work through those 3 options. If I perform the query at site 1, what do I need to do? I need to grab the data from site 2, send it to site 1. So the data from site 2 in this case is the department data. What columns do I need from the department table? Based on the query, it looks like I need the department name and the manager's social security number, right? Those are the 2 columns that I need. So That's going to be 9 bytes for the manager's social security number plus 10 bytes for the name. That's 19 bytes total times 100 records. So that's 1900 bytes, correct? To send the data from site 2 to site 1. I'm then going to perform the join. I'm going to perform the join. So how many records am I going to have after the join in this particular query? What is this query asking us for in English? If we had to describe what this query is going to show us in English, what would it say? Anybody have an idea? Yeah. The first name, last name, and department name for each manager, right? For each department manager. So how many rows do I expect in my result? 1 row for each. 1 row for each department, or 1 row for each manager. This is implying that there's 1 manager for each department, right? At the most, there's one row for each department. So the number of rows in my result is going to be fairly small, right? It's going to be 100. Because there's 100 records in the departments table. And how big is my result? It's based on the first name and the last name and the department name. So it's 40 bytes. 40 times 100 is 4,000. So I'm going to have 4,000 bytes after the join. Does that make sense? Everybody on board with me on that one? So that's if I perform the join at site 1. If I perform the join at site 2, it's similar arithmetic, but a little bit different. I still have the 4,000 bytes after the join, right? But now I need to figure out the cost of sending the columns from the employees table to site 2. So I need to send the first name, the last name, and the social security number column. So that's 15, 15, and 9. So 39 bytes times 10,000 records. It's going to be 390,000 bytes. And then the last scenario that we have is site 3. If I want to do the query, if I want to do the join at site 3, I'm going to send 1900 bytes from site 1, and I'm going to send 390,000 bytes from site 2. So now these numbers paint a very interesting picture, right? The best place to do the join for this query is site 1. I don't even need to add these up. It's very obvious just from looking at the numbers. The best place to perform this query is site 1. Why? Because the result from the join is very small. The result from the join is very small. So it makes sense for me to send the data to the site with the largest amount of stuff, perform the join there, since the join result is small, and then send that back to the original site. Yes?
How would the computer know that the result is small?
That's a good question. How would the computer know that the result is going to be small? Can the computer figure out these numbers ahead of time? What do we think? Is that possible? Yeah.
Not exactly, but like
with the heuristic maybe. So I think actually in some cases the answer is yes, absolutely the computer can figure these numbers out ahead of time. The computer knows how many rows are in each table. I don't think that's an unreasonable thing to know, right? The computer knows what the columns are and what the data types of those columns are, which dictates maybe not the exact size, but at least gives us some idea of what the size can be. If I'm worried about string columns, I can just assume they'll all be max size, perhaps, right? Is that inaccurate? Maybe, but for the purposes of calculation, it's good enough, right? So I actually think that in some cases the computer can figure these out. Can I figure out how many rows are going to be left after a join? If it's a one-to-many join and I expect full participation by one of the sides, then yes, actually, I can figure out how many results are going to be at the end after a join. I can determine that. So yes, I think the computer does know all the pieces that it needs to run these computations. There are cases where that might not be true. That may not be possible. What if I expect, some of those values not to have a foreign key, right? That's going to change things a little bit. It's going to change my computations a little bit. But even if that is the case, it only makes the numbers better, right? This is maybe a worst case scenario. This is maybe a, an upper bound in that sense. And I might get away with less, depending on the situation. If I'm doing something different where, if we think about very complex queries where I have maybe an additional set of conditions that I need to evaluate, then it becomes trickier, but we can rely on the concept of, what was that called? When I remember how many rows are going to meet a certain condition. What was that called? I'm sorry? Not caching. It's a similar idea. Rhymes with electivity? I don't know. Selectivity. I can use the selectivity of the conditions to help me determine these things. Again, is it going to be 100% accurate? Not necessarily, but one thing I think you can take away from this example is that the numbers are actually very far apart from each other a lot of times. So it should be fairly obvious, right, which one is the better choice. There's no contest here. And if it's close and I picked the wrong one, well, who cares? I lost a little bit, but it was close. So it's not going to make a huge difference either way. Yeah?
So does it not actually matter where the query is being submitted from?
Just where we're performing? That's a great question. So does it matter where the query is being submitted from? That's actually what the next problem describes. So let's take a look at that one real quick. In the previous examples, we assumed that the queries were being submitted from a third site. But what if the query is not being submitted from that third site? What if it's just being submitted at site 2? So there's only 2 sites in this example. The third site is gone. It's no longer true. So one thing that we have to understand is if I submit the query at a location, the results have to make it back to that location, right? I'm not going to submit a query at site 2 and send the answer to site 7, right? I submitted the query at site 2 because that's where I want the results to be, at site 2. So in that sense, it does matter. If we rerun even this past example with the idea that site 3 is no longer in the picture, right? We're going to get different numbers back out. Because in this particular case, site 3 is gone, so we can just erase this scenario altogether. That's not even a scenario that exists anymore, right? The numbers for site 1, so send the department's data to site 1, send the join values back. That actually is still correct, right? For site 2, I don't need to send the join data anywhere. I just need to get the employee data where I am, right? And then perform the join. But even after taking out that factor, it's still better for me to send the department data to site 1, perform the join there, and send the data back in terms of bytes transmitted. Think about that for a second. It is better for me to take 2 trips rather than just 1 trip, because the amount of data being sent from the employees table is so large, it actually makes more sense to send the smaller amount of data over and then send the smaller amount of data back. Now, some of you might argue with me, well, there's, the overhead of making the network connection, right? And if I have to do that twice, that's going to be more than if I just have to do it once. And you're right. You're right. That is true. Those are things that we would also want to take into account. I never claimed and will never claim that these kinds of problems will be definitive in terms of the behavior that we should do. But if we're only focused on bytes sent, if that's the metric we're concerned about, this is how the computations work out. If you want to take other things into account, like network overhead, how loaded are the servers? Can the server perform the join, or is it too busy? Am I going to get bogged down? Right? That's a different problem. Certainly a problem worth solving, but a different problem. Different problem to talk about. Great question. Any other questions on this before we put it aside and continue with the material? Any other questions? All right, fantastic. Well, then I've got a few loose ends to tie up about distributed databases, and then we'll do some more practice problems in just a little bit. So, first, let's talk about decomposition. So decomposition is something that we need to take into account when we have replication at play. So if I have multiple copies of the data, which one should I use? Which copy should I use? It might seem like a silly question, like, does it matter? Can't I just pick whichever one I want? And the answer is yeah, but actually from a performance perspective, some copies might be better than others. Why? What criteria might help me decide which copy I want to use? If you're a database, you've got 3 copies of data that you could choose from. What information are you going to use to help you decide which one you want to choose? Your goal is to get it as fast as possible. So what are you going to look for? Yeah.
How close?
How close it is. Yeah. Where's the data? Is it at the same machine I'm at? Well, that's a no-brainer then, right? I don't have to go anywhere. It's right there. If I do have to go somewhere, which one's closer to me? Which one's closer to me? So that's one piece of information. What else might you look at? What else might you look at? It can get a little more complicated than that. Yeah. Which one was updated most recently? So if I'm worried about things like consistency, now, actually in a traditional relational database, we have to worry about consistency, but I'm never worried about the case where data is not consistent with each other because we will aggressively use locking. We're going to talk about that in a little bit. Aggressively use locking to maintain consistency. But that could be a policy, right? Which one has been updated most recently? Think about it in terms, too, of the larger picture. I need this piece of data, but maybe I need some other pieces of data as well. Can I find a place that has everything that I need? Or do I need to go to multiple locations to get all of the stuff that I need, right? It could be useful to look at the larger picture. If I can go one place and get everything that I need, it might be better for me to do that, even if it's a little bit farther away than where half of the data is, right? Because then I have to make 2 trips, and that's going to be slower. So that's another thing we can take a look at. Updates, right? Has a similar kind of thought process with one additional wrinkle on it. Actually, you could argue that reads have the same kind of wrinkle on it as well. If I want to update a piece of information, what do I need in order to do that? What am I required to have before I can update a piece of information? What are you working on right now for homework 4? Lock. I need a lock. I need a lock, right? So how do I get that lock? Where do I go to get that lock from? That's actually something we're going to be talking about in a little bit. But, how I need to acquire that lock, whether I can acquire that lock or not, is going to help me answer the question of which copy I should try to grab. So we're going to talk about that in just a little bit. But where's all this information actually being stored? How do I actually even answer these questions in the first place? How do I know how many copies I have? How do I know where those copies are? Where am I going to find that stuff? What is that an example of? That information, yeah. Not an index, but we're getting a little warm. Metadata, yeah, metadata. It's metadata. It's metadata. So metadata is stored where? It's in a table, but where's the table? Or how do I access that table? Rhymes with catalog. Oh, I don't know. It's in the catalog. It's in the catalog. Is there a word that rhymes with catalog? There probably is. What? No. Unrhymable word. I don't think that's true, but maybe it is. All right. So we're going to go to the catalog. We're going to ask the catalog, hey, how many copies of this thing are there? Where do those copies live? But that becomes a problem too, right? That becomes a problem too, because there's only one copy of the catalog, or is there? I don't know. That's something we're talking about. And so now the catalog can become a bottleneck. If everybody has to go to the catalog to answer these questions, then the catalog has to be able to keep up with all of those requests. And that could become a potential bottleneck. That could become a potential source of slowdown. Before we solve that, though, let's talk about something else related to distributed databases that is close to what we've been talking about recently. transactions are now not necessarily going to be in one place, but spread out across multiple places, right? If I submit a query, even like the queries we were just talking about that require us to join two tables that live in two different places, I'm taking that transaction and I'm splitting it up into those different places so that I can access the data, correct? And so we need a way to coordinate those transactions across those different locations. And the classic way of doing that is with this idea of a global transaction manager. There is one place that is going to manage all of the transactions. So if I spin up a new transaction, it's got to go through this global transaction manager. The global transaction manager will act as a middleman between all of the satellites, right? And so one way that this is proposed is to use what's called a two-phase commit. I can't just commit all in one step now. I don't want to commit until I know that all of the satellite pieces of my transaction are ready to commit. Correct? What property of transactions are we following when I say that we need to make sure all the pieces are ready? I can't just commit this satellite when it's ready, because then I would only commit part of the transaction, right? Instead of the whole thing. What property is that? Transactions are all or nothing. What property is that? Yeah, atomicity. Atomicity. Transactions are atomic. I have to treat the whole thing as a single unit. The global transaction manager exists to help us enforce that atomicity when our transaction is in multiple locations, in multiple spots. So it's going to coordinate this process. It's going to talk to all of the different satellite spots where the transaction is occurring. And when the transactions are ready, it will let the global transaction manager know that it's ready. That's phase one. Phase one is all of the satellite transactions. They'll actually write everything onto the log, right? They won't actually commit the data yet. So the data is sitting in memory, ready to be written back to disk. It sits there and it waits and tells the transaction manager, like, okay, I've made all the changes. I'm ready to write this data to disk, but I'm going to wait and make sure, right? I'm going to wait and make sure that everybody else is ready. I'm going to wait for you to tell me that everybody else is ready before I actually take these changes and push them to disk. So the global transaction manager will be communicating with everybody as soon as it hears from all of the satellites that they are ready. Their data has been updated. They're ready to write it back to disk. It'll send out a message to everybody that says, all right, go. Do the commit. At which point they will take the data that's been changed in memory, write it back to disk. They'll update the log indicating that the commit has happened, and those changes are now permanent. Those changes are now part of the database. And this is pretty good, right? In a general sense, it kind of seems to solve the problem that exists, a lot of the problems that exist when we have to split our transaction up into multiple places. But there are some problems with this approach. Consider what would happen if the global transaction manager were to crash for some reason. It could happen, it could fail. There are some parts of this process that are worse than others in terms of failure, right? Consider if the global transaction manager were to fail either right before or right after sending out that message telling all of the other places to commit. So it tells everybody, all right, we got the go ahead, everybody's ready, do your commit. And then it crashes. And then what if maybe some of those satellites also crash? Do we know if they got the message or not? Do we know if they performed the commit before they crashed or not? The remaining sites are sitting there and they're in this kind of limbo. Maybe those other ones committed before they crashed, maybe they didn't. But what should I do? If I assume that they did the commit, then I should perform the commit, right? Because we want everything to be the same. Either everybody does it or nobody does it. If I assume that they didn't do the commit, then I should abort and roll back my changes as well. But I have no way of knowing. I have no way of knowing if that's true because they crashed. And the global transaction manager is also down. So I can't even go back and ask it if everybody's performing the commit or not. And so there's actually an additional phase. Two-phase commit works pretty well, but it's not failure resistant enough for our purposes. We're going to break the commit process into 3 phases. The first phase is actually the same for both 2 and 3 phase commit. Phase 1 is the same. The individual sites do the work, and they sit there with everything in memory, ready to commit, but they're waiting. They're waiting for the global transaction manager to tell them that it's okay. The second phase then gets split up into 2 pieces. There's a prepare to commit. So this is now a 2-phase process. The global transaction manager says, all right, I think we're ready. Are you guys ready? It's basically a double check. Like, you're okay? You're sure? You're ready with this? Everybody else is ready. I'm ready. Are you still ready? And then the participants will vote. They'll say, yes, I'm ready, or no, I'm not. And if anybody votes no, the whole thing fails. If everybody votes yes, then everybody commits, right? But the very act that we've split this up into 2 phases, right, now tells us that at least everybody thought they were ready to commit at one point in time. And it should make it a little bit more fault tolerant. Now, if the global transaction manager were to crash, we can simply ask our neighbor, hey, did you get the message? Did you get the message to commit? And if they did, we know that everybody voted yes, and so we should go ahead and proceed. And if they didn't, we know that at least somebody voted no, or the message didn't get sent, and we should abort. In other words, we're taking some of the information and distributing it out to the participants. In case the global transaction manager were to fail, those participants can talk amongst themselves and determine what to do. That was what was missing from the 2-phase commit process. So this 3-phase commit is now a standard, actually. This 3-phase commit is the standard for handling transactions across a distributed database. Are there any questions about that? Any questions? All right. The last thing to talk about, is concurrency control. Concurrency control being things like locking. How does locking work under a distributed system? So here are some potential problems with related to locking when dealing with a distributed database. I have multiple copies of the same data. How do I treat locks when I've got multiple copies out there? How do locks work when I have multiple copies of the same piece of data? What if I lock a piece of data and then one of the sites fails? What do I do then? Can I still make updates? Is that something that's possible or not? What if the communication fails? What if I'm making an update, and as part of that update, I'm updating all of the copies, but for some reason or another, the update just doesn't make it, right? The communication failed. Now I've got a problem of consistency, right? Something else that we need to be worried about. Distributed commits, that's actually what we just talked about with transactions. So that's 3-phase locking. Distributed deadlock is an interesting case where if I have locks that are distributed across multiple databases, now I can actually have deadlock that occurs across multiple sites as well. The good news about distributed deadlock is that the solution to it is actually almost the same as non-distributed deadlock. We just need to have some place that is monitoring the transactions in all locations, which is not an easy thing to do, right? The global transaction manager is doing a large part of that for us. So it sort of falls to the transaction manager to resolve that kind of deadlock. I'm more interested in talking about the first few problems, though. How do we handle locking with multiple copies of the same data? So one proposed solution is to use what's called a distinguished copy. A distinguished copy. So if I have 3 copies of the same piece of data, I'm going to mark one of those as a distinguished copy, and then any request for a lock has to go through that copy. So if I hold a lock on the distinguished copy, I hold a lock on all of the copies. In some sense, this sounds reasonable, right? I don't want to have to ask, if I have 3 copies, I don't want to have to ask for 3 locks. That's kind of ridiculous, right? It would take a lot of work. So by using a distinguished copy, I can ask for 1 lock and acquire the locks for all of them. So how do we choose these distinguished copies? Where do these distinguished copies live? The simplest case is to say that all of my distinguished copies live in one place. So I have one centralized place called a coordinator site where all of the distinguished copies live. What's the downside of that? I put all my distinguished copies in one place. What's the problem with that approach? Yeah. I'm sorry? If that place fails, I'm in big trouble. Or even less severe, right? All of my locking requests now have to go to that place. So that server is going to get hit hard with locking requests, right? Coming from all directions. So there are other ways. So what I just described was a primary site. There are other ways of dealing with this. I can designate a backup. So yes, I have a primary site, but I designate you as the backup. If the primary site fails or the primary site is unavailable for some reason, the backup steps up and becomes the new primary site. The downside of that is that now I actually have to have the backup site mirroring the primary site, so I'm taking up more space. That's an additional copy of data, right? That's more space that I'm taking up. Or another way of doing it is to say, well, maybe we don't have to put all the distinguished copies in one place. Maybe I can spread them out. So the distinguished copies can live on different locations. They don't have to be on a primary site. I can have a primary copy, which could be anywhere. What's the problem with that? What's the downside of letting my distinguished copies be distributed across the entire system? Yeah. Now I'm back in the position of having to go multiple places to acquire the locks that I need to perform the operations that I want. So it's a trade-off, right? It's a trade-off. The distribution helps with the availability, but is going to increase the amount of communication required for me to do my job, which is going to take more time, right? So there's another way of thinking about it. We can now do a voting method. There is no distinguished copy. With the voting method, there's no distinguished copy. Every copy has a vote. Lock requests are sent to all of the items, and each item will vote. Yes, you can have the lock, or no, you cannot. No, you cannot have the lock. And it'll use whatever reason it needs to decide, right, whether or not it can have the lock. It might decline because somebody else already has the lock. It might decline because, honestly, it's just too busy right now to even grant you the lock, right? That's valid as well. In order to actually acquire the lock, we actually do not need all of them to agree. We only need a majority to agree. Think about that for a second. Think about why that's true. It might be a little bit surprising, right? That we don't need all of the locks. We actually just need a simple majority. If I'm trying to acquire a write lock, and there are 3 copies, I only need 2 of them to agree to give me that lock. Because even if somebody else were to come along and try to acquire a write lock on the same thing, they could acquire 1 of the 3, but there's no way they'd be able to get a majority because these 2 are not going to give them that lock. I already have it, correct? So a majority is enough. And that gives us some flexibility. If one of the copies goes down for some reason, I can't communicate with it for whatever reason, right? As long as I have a majority, that's still okay. And then whenever that copy comes back up, we can resolve any issues at that point in time. We can get it up to speed if necessary. So a simple majority is what's necessary. This is a very truly distributed way of handling the situation. But the main disadvantage of this is what? It's just an even worse example than the primary copy situation. Here I'm sending a very large amount of messages to acquire locks, a very large amount of messaging traffic. So communication becomes a very big part of this. That could still be viable. Maybe your network is very good. Maybe all of your machines are very close to each other, so network costs aren't very expensive, right? Maybe that's acceptable. Depends on how your system is set up. All right, cool. Last, but certainly not least, earlier I mentioned the idea of catalogs. Catalogs are a very, very important part of not just a distributed database, but any database. So, how do we track this catalog information when I've got multiple sites? And there's basically two schools of thought here, and it's a very kind of reoccurring theme with distributed databases. I can have one catalog in one place, or I can have a catalog that is replicated, copies of that catalog across many different locations. And the trade-offs are similar to trade-offs that you would expect in other situations where I can centralize or distribute something. If I replicate the catalog, what's the drawback? What do I need to pay attention to? I don't just have one copy of the catalog, but I have 10 copies now. What's the price that I pay for that? The updates. Anytime the catalog changes, I now have to change all of the other ones. I have to change all of the other ones. So if the catalog is managing lock requests, if the catalog is managing the locations where my replicas live, and one of those things changes, right? I now have to make sure that all of the catalogs have those changes as well. That's not to say that centralized catalogs are absolutely the best option either, because now that becomes a bottleneck, a potential bottleneck, right? There's only one place. Or what happens when the centralized catalog goes down? Now my entire database is unusable because I cannot access the catalog. Whereas if I have 10 copies, I can just go to a different copy, right? And access it there. Again, what's the best situation? It really depends on what your needs are and the capabilities of your system. What is your system capable of delivering? All right. That's it. That's all of the information about distributed systems that I have to discuss with you. The rest of today, so just to give you a heads up, I've got 8 or 10 slides of practice problems here. We probably won't get to all of them. We have about, 40 minutes left. We probably won't get to all of them, but I would like to do as much as we have time for. Does anybody have any questions before we do that? Anybody have any questions at all? All right, so I've got a couple slides of just basic review. So here's what I want to do first. There's 2 slides of review questions here. I will leave these slides up on the screen and give you a few minutes to talk to your neighbors about them, and then we'll discuss them together as a group. Take a few moments. I'll be around if you have any questions. We'll chat about these in just a little bit. So if I have a majority of blocks, anybody else so for somebody to have a read block, they also need to have so there is race conditions. That's just the condition. And that's what you do by where is a best careful catalog management. Race conditions are always
Reliability is like no, it doesn't. catalog that's available, yeah, percent, measure video, 5 minutes per year, staff. Like your properties, well, they can be available once distributed because you can just take down certain copies. So distribution increase the availability.
So the availability is how long we
Yes.
the distribution would give one server goes down, you still have
Yes. But
especially if
what
you
you
have a
need
copy
to
of
do for maintenance, what you need to update all of
not if your data is just compared, so they aren't all strict copies. That's a it's just say students is on one teacher. No distribution. Get the 5%.
All right, let's have a little chat about these real quick before we hop into the next round. One advantage and one disadvantage of replication. So what's an advantage of replication? Why do we replicate our data? What's the point? Yeah. So it can be a backup copy. Yeah. Any other advantages? Yeah. I can get to it from multiple locations. What's that an example of? That's actually related to another question up here. It is distributed. That's true. Yeah. Accessibility or availability, actually. Yeah, availability. Having multiple copies of data increases availability. That's actually a potential answer to the last question, right? Multiple copies increases availability. It means that if one spot goes down, well, I still have another copy up, so my system remains available. What's the disadvantage of replication? Yeah. Consistency. And also, what's another disadvantage? Space. I'm giving up more space for it as well. All right. This one we kind of just talked about a few minutes ago, right? About the distributed catalog. When would we want to use a distributed catalog as opposed to a centralized catalog? What conditions would lead us in the direction of using a distributed catalog instead of a centralized one? When would that seem like a good idea? Yeah. So, okay, yeah. So if failures are and actually this kind of relates to availability again, right? If the catalog goes down, the whole database is unusable at that point, right? So if I have a centralized catalog and it goes down, my database is unavailable. So if I'm trying to maximize availability, which is generally seen as a good thing, generally seen as a desirable outcome, then distributing the catalog makes sense. Is there a cost? Yes, absolutely. There's a cost. There's a penalty for that increased availability, but everything has a price. Everything has a cost. Can you think of any other situations that would lead us in the direction of using a distributed catalog as opposed to a centralized one? Yeah.
we did the catalog a lot, but we're not changing it.
So if we're not changing the catalog very often, good. If we're not changing the catalog very often, then the penalty that we incur for updating it becomes less of a factor. So we might actually see an increase in performance as an effect of distributing the catalog, right? Good. All right. And so we've talked about availability a bit and how distribution affects availability, but let's talk about reliability. Yeah. Why would we use a centralized catalog? So if my catalog is changing a lot, if I'm making a lot of writes to it, a centralized catalog is potentially going to be more efficient because I don't have to worry about consistency in that scenario, right? If I'm worried about security, it's much easier for me to protect something if it's only in one place as opposed to 10 different places, right? That could be an argument for using a centralized catalog. I'm exposed a little bit less. So let's talk about reliability a bit. How is reliability different from availability? How is reliability different from availability? This is a classic exam question. How would I measure reliability? Does anybody know? Yeah. Mean time between failures. That's right. So availability is usually measured as a percentage. How much of the last 10 years, right? How often did my system crash? Or not crash? How often was it up? However you want to describe it. Mean time between failures is more of a predictive model, right? I expect to have problems with this system at least once every 5 years, right? That's what mean time between failures is trying to tell us. So just like distribution affects availability, it also affects reliability. If I have more machines, I become more tolerant of failures, which means the amount of time that I expect between total system failures is going to increase, which is going to be better for us, right? Think about it this way. If I have one machine, the mean time between failures is equal to the time, the expectation that that single machine will fail, right? So if I expect that machine to fail in 5 years, my mean time between failures is going to be roughly 5 years. If I have lots of machines, now the mean time between failures of the entire system is the chances that all or a significant portion of those computers fail at the same time, right? Because if only one of them goes down, I can have the other ones pick up the slack and then get in there and fix it. So now my reliability has also increased. Is it still possible for multiple machines to fail at the same time? Sure, absolutely. But the odds of that happening are much smaller than if I'm just relying on a single machine, a single system, a single site. Does that make sense? Are there any questions about that? All right, let's take a look at a couple more questions. Just like before, I'm going to give you a few minutes to chat with your neighbors about these guys, and then we'll have a talk about them together. Okay. So this first question we actually talked about recently, just a few moments ago. If I'm using replication, I have to decide what replica I want to use. So what information is the database going to use to make that decision? Just chatted about this a few moments ago. I have to decide what copy I want. Yeah. The data transfer cost. So what's going to determine that then? How am I going to determine that information? Because I might not actually know what that information is off the top of my head. I might be able to figure it out, but what am I going to use to figure it out? What information do I expect to have on hand to help me answer this question? Location. Where is it? Where is it? Which is going to tell me how far away it is, perhaps, right? So that'll go into the data transfer. Sure, yeah. Can we get it all out of one place or not? Or do I have to go to multiple places? I'd like to minimize the amount of trips that I have to make if possible. Yep. This last one is actually more related to what we talked about on Monday. So if we don't have any replications, so replication's out the window, and I'm partitioning a table, which partitioning scheme is going to take up more space? Vertical partitioning or horizontal partitioning? Anybody know? I'm sorry? The vertical partitioning. Why?
Because
We need the primary key in both locations. So actually, I cannot create vertical partitions without duplicating the primary key. It's not possible. With horizontal partitioning, I don't need to duplicate any of the data, right? I can if I want to, but I don't have to as part of the partitioning scheme. With vertical partitioning, I have to replicate that primary key column. Good. Any questions about these review questions? Actually, all 5 of these questions that we just did were past exam questions. All 5 of them were past exam questions. All right. This problem is very long, but the actual question itself is kind of short. So take a moment. Can you guys even read? Yeah, it's not that small. Take a moment to look over this, and I'm gonna do like 1, maybe 2 laps around the room, and then be ready to tell me what kind of fragmentation is being used in this scenario. All right, what kind of fragmentation are we using in this example? We got 2 different kinds. Are we using vertical fragmentation here? Yes, I see somebody saying yes. Which part of this problem is describing vertical fragmentation? Which part? The second. So each product has information about how much our company paid for it, as well as how much we wish to sell it for. We only need that at company headquarters. We don't need it at the shipping center. So that means the shipping centers has some of the information about the products, but not all of the information about the products, right? That's an example of vertical partitioning. Vertical partitioning. What about horizontal partitioning? I see at least a couple people saying also yes to that one. So which part is telling us about about horizontal partitioning? It would be the first one. So we have 2 shipping centers, one for video games, one for computers. So all of the video game stuff's at the video game site, all of the computer stuff's at the computer site. So those are both part of the same table, right? But some rows are going to be in some locations and some rows are going to be in another location. That's an example of horizontal partitioning. What about this last point? So we talked about the first 2 points. What about this last point? Is that an example of vertical or horizontal fragmentation? It could be. Could be an example of what kind of fragmentation? Vertical? I would say, well, is it an example of vertical part? I'm kind of doubting myself now. Kind of doubting my own answer to this question. Is there any vendor information at the company headquarters? The problem makes it sound like there's not, right? It's only at the shipping centers. It says it's, this vendor information is only kept at the shipping centers, not company headquarters. So that's maybe not even an example of partitioning at all. That's just 2 tables being kept in 2 different places. I'm not chopping up the vendor's table necessarily, or am I? Actually, I have the same table in 2 spots. Didn't I just say that? So if I wanted to get all the vendors in one place, what would I have to do? Would I have to join the information? There's 2 options. If I have vertical partitioning, how do I stitch the data back together? I use what relational operation? Vertical partitioning. I want to combine it back together. That's a join. That's a join on the primary key. If I have a horizontal partition and I want to stitch that data back together, what do I use? We haven't talked about this operation as much, but we have talked about it a little bit. How do I stitch the horizontal fragments back together? It's an operation. It's a set operation. I'm sure you learned about in discrete math, probably. Rhymes with reunion? I don't know. That's a bad example. A union operation will stitch the horizontal fragments back together. So actually, this, I believe, is an example also of horizontal fragmentation. 2 examples of horizontal fragmentation here. 1 example of vertical fragmentation. Does everybody understand that? Yeah.
So we were talking about vertical, but for B fragmentation, do we need a full copy anywhere?
Do we need a full copy anywhere? No, you don't.
Right. So then why wouldn't vertical be vertical?
It's not vertical. I would say it's horizontal, probably, would be my guess. It'd be horizontal.
So I was thinking each item would just have a vendor field.
Oh, I see. So I guess we're just envisioning this in different ways. Right. I'm envisioning this as a whole separate vendors table with information about a vendor. That's what I'm envisioning.
So then if it were, okay,
and then the vendors that are related to video games are over here, and the vendors related to computers are over here.
So you're talking about 2 different tables.
I'm talking about 2 different pieces of the same table.
Well, no, but like the items table.
Yeah, there's a products table and a vendors table. That's how I envision this problem, but you were making the statement that you thought vendor would just be like at a field on the product. Now, that could be, right? There's certainly nothing that would stop us from doing that, but that would be an example of poor normalization. Yeah, not a very well normalized database in that particular case, because I'd have the same vendor showing up many different times for many different products. So could it be that way? Yes. I hope not, though. I really hope not. All right, cool. So there's a follow-up to this example that's very similar to the ones that we just did about data transfer costs, right? I've given you this query and information about it. My advice to you on this one is to, excuse me, look very carefully at what's being asked of you and remember the setup that we just discussed about where the data lives on the prior, on the prior slide before you start figuring this one out. So make sure you understand exactly what's being asked of you before you start figuring out numbers here. I'm going to give you a few minutes, talk to your neighbors, and we'll do this one together in just a little bit. So when you're faced with a problem like this, right? If I ask you a question like this on the final exam, for example, first thing you should consider is I've got a join here, and so really what this question is asking us is, where should I perform that join? Where should that join take place? That's really what questions like this boil down to. And I have three options in this case. I can perform the join at headquarters, I can perform it at site 1, and I can perform it at site 2. But if you read this problem carefully, I think one of those options is far superior than the other two. Does anybody know where this join should be performed? Should I perform it at headquarters or one of the shipping centers? Think about what information each site has. Think about what information each site has. Company headquarters has information about all of the products already, right? All of the products already. It does not have any of the vendor information. It does not. So the shipping centers have the vendor information, and they also have the product information, but they don't need to send the product information to company headquarters because company headquarters already has it. So in that case, considering that we would need to send a lot more data from headquarters out to the shipping centers, since I need to include product data, right? It makes a lot more sense to perform the join at company headquarters in this case. At headquarters. So the total data transfer cost is actually just going to be based off of the cost of sending the vendors table to headquarters. And so what columns do we need from the vendors table? We need the vendor ID. We need the vendor name. I think that's it. Vendor ID is 4 bytes. The vendor name is 10 bytes. How many rows are in the vendors table? 50 rows. Are those rows all in one place? Not necessarily, actually. We just talked about that. This last point here indicates that, well, I don't know. I guess you could interpret that either way. It's a little ambiguous. Now that I read it again, this is a little ambiguous. Is it a different? I don't know. Is there horizontal fragmentation going on here or not? I don't know. But I think it doesn't matter. I think for the purposes of this problem, it doesn't matter if there's horizontal fragmentation going on or not. Because either way, I'm sending 50 rows. It might be 25 from each. It might be 10 rows from here, 40 rows from here. It might be all 50 from here and none from here. I don't think it matters because at the end of the day, I'm sending 50 rows of vendor information with 14 bytes a pop. So that's going to be 700 bytes. 700 bytes of data. I don't think we even need to compute the costs for the other ones. I think it's somewhat obvious from the way that this data is laid out that that is going to be the best outcome. If you want to go through it as an exercise, that would be fine, right? But I don't think it's necessary. I feel confident in saying that is going to be the best. That is going to be the best possible situation here. Are there any questions about that problem? We got about 10 minutes left, so we're not going to have enough time to do all of these. The rest of these actually have more to do with what we talked about in the past. I've got some about locking. I've got some about scheduling. Does anybody have an opinion as to what you would like to spend the remaining time on? Would you like to do a scheduling problem? Would you like to do a locking problem? What would you like to do? Somebody tell me what to do, or I'll just randomly pick one. No opinion one way or the other? I'm going to do a locking one then. This is probably the last one that we're going to have time to talk about. We're running a little short on time. I'm giving you this schedule here, right? I'm giving you this schedule. I want you to insert locks into this schedule such that it satisfies strict two-phase locking. So that's step one, right? And then once you've done that, I want you to, answer this question. Are we going to suffer from deadlock? Is this schedule serializable? Take a few moments. Talk to your neighbors. Sketch out what you need to do to answer this problem, and we will discuss in a few minutes. Okay, we are running out of time. Let's see how far we can get with the few minutes that we've got left. We want to insert locks using the strict two-phase locking protocol. So, quick review of that. When I say strict two-phase locking, what is that telling us to do? What are the restrictions placed on us by strict two-phase locking? I hold on to my write locks until the very end of the transaction. I can let go of my read locks sooner if I want to, right? Hold on to my write locks for the whole time. And then the two-phase locking just in general says what? Phase one is hoard locks, right? Grab them all. Phase two is let them go. So I have to acquire all of the locks before I can let any of them go. So actually, when I ask you to insert locks, there are a lot of different ways that you could decide to insert locks here to satisfy strict two-phase locking. There are a lot of different ways you could do that. And the answer to the second question, explain whether your schedule would suffer from deadlock or not, depends very much on how you decide to insert your locks for two-phase locking. So I'm going to sketch some stuff on here to insert some locks. You could have made totally different decisions, right, on how to insert those locks and still obeyed strict two-phase locking. That is entirely possible. But one thing's for certain, I have to have the lock before I perform a particular operation on a given item. So I would have to have a read lock here, right? I'd have to have a read lock on Z before I read that item. And I have a read on Y followed by a write on Y, and I think most people would probably say, well, skip the read lock, just grab the write lock. So I need to have a write lock on Y before I do these two operations, correct? And once I have that write lock, I am now hanging on to that write lock for the entire length of the transaction. I'm not letting go of that write lock until I get done with everything else. So think about what that means. I'm going to get down here. If I look at transaction 3 now, I read item Y, and actually, at this point, it's too late for me to even acquire that read lock, correct? It is not possible for me to acquire that read lock, correct? So transaction 3 has a problem. It's going to stall out. It might it also can't acquire the write lock for item Z as well. So it can't acquire any of the locks that it wants to. Can't acquire any of those locks. Well, let's look at transaction 1. Can I acquire the write lock on X? Yes, I can. Can I acquire this write lock on Y? Not until transaction 2 is completely finished. So actually, is this even a realistic schedule? No, it's not possible for this schedule to work. It is not possible for this schedule to work because transaction 1 is going to be waiting on transaction 2 to release the write lock on Y, and transaction 3 is also going to be waiting for that, as well as the read lock on Z. So the fact that transaction 2 grabs those locks early prevents transaction 1 and transaction 3 from being able to perform its tasks. Actually, we could release the write lock on Z, though, here, right? Release RZ. We could do that there. I'm allowed to, I'm allowed to release read locks early if I want to. So that could free up at least part of transaction 3. But I think the issue that we're going to run into with this schedule is based on data item Y. Transaction 3 nor transaction 1 are going to be able to acquire that lock until transaction 2 is finished. Is this really an example of deadlock, though? Not necessarily. It's just an example of a bad schedule. A schedule that cannot follow the two-phase locking protocol. Right? This schedule would never happen. If we're obeying the strict two-phase locking protocol, this schedule would never happen. It would never happen. I would have to do these items first, and then I could start doing either transaction 3 or transaction 1 if I wanted to. So strict two-phase locking is slowing us down. A good exercise that might be worth taking the time to do. We only have a minute left, so we're not going to have the time to do it now, but good exercise might be to say, all right, What if we just obey basic two-phase logging? Then could I pull this schedule off? That would be a good exercise, right? What if I take the strict requirement off? Then could I obey this schedule? That would be something worthwhile. Unfortunately, we don't have time to do that right now, though. Does anybody have any questions for me before we wrap up? Any questions at all? All right, I'm really looking forward to Monday. We're going to talk about something totally different. It's very exciting, very cool topic. Have a great weekend, everybody. I will see you then.